At 6:35 in the morning, Coordinated Universal Time on August 5th, 2026, a piece of SpaceX hardware that had been quietly drifting through space for a year and a half finally reached the end of its journey, slamming into the moon's near side at more than 5,400 miles an hour, close to the Einstein and Bell craters. It was not a mission. Nobody planned this specific impact, and nobody aimed it. It was the spent upper stage of a Falcon 9 rocket, launched in January of 2025, still drifting through cislunar space 18 months after its job was finished, until solar radiation pressure and the moon's own gravity did what neither SpaceX nor NASA had originally intended, and pulled it home to a target nobody chose. This actually happened 2 days before this script was recorded, and there is real data behind every part of it, tracking calculations. From an amateur astronomer working from publicly available orbital data, a 100% confirmed impact probability from NASA's own Center for Near-Earth Object Studies, a detected flash of vaporized metal caught by one of the most powerful telescopes on Earth, and genuine before and after images of the impact site captured by a lunar orbiter belonging to South Korea's space agency. I want to walk through exactly how this object ended up on a collision course with the moon in the first place, since that story says something important about how much space debris humanity has already scattered around our nearest neighbor. I want to explain precisely what instruments on Earth and in lunar orbit actually managed to observe, because the honest answer is more interesting, if less cinematic, than a dramatic explosion caught on camera. And I want to place this single event inside the broader and genuinely underregulated problem of what happens to rocket stages after their mission ends, because this was far from the first time it has happened, and it will not be the last. Start with where this specific piece of hardware came from. On January 15th, 2025, a Falcon 9 rocket lifted off from Kennedy Space Center's historic Launch Complex 39A, carrying two separate lunar landers riding together toward the moon, Firefly Aerospace's Blue Ghost Mission 1, and iSpace's Hakuto-R Mission 2, also known as Resilience. The mission itself had a genuine Y mixed outcome. Blue Ghost went on to make a fully successful soft landing on March 2nd, 2025, becoming one of the first fully successful commercial moon landings in history. Hakuto-R was far less fortunate, losing contact roughly 90 seconds before touchdown in June of 2025, an anomaly iSpace's engineers later traced to the spacecraft's laser rangefinder, resulting in a crash landing rather than the soft touchdown the mission had planned for. Once both landers separated from the rocket and continued on their own paths, the job of the Falcon 9's upper stage, the second stage, that does the work of actually propelling a payload the rest of the way after the reusable first stage returns to Earth, was finished, with its fuel essentially spent completing the translunar injection burn that sent the landers on unstable orbit somewhere between Earth and designation 2025-0110D. According to SpaceX's own account, the company followed standard disposal procedures for the stage at the time. What nobody fully accounted for was just how unstable that particular orbit would prove to be over the following 8 to 10 months, as the combined pull of solar radiation pressure and lunar gravity gradually bent its path, degree by degree, until it was no longer missing the moon at all. The person who first spotted where this was heading was not a government agency. It was Bill Gray, an amateur astronomer who has built a long-running reputation for tracking exactly this kind of object, using publicly available orbital tracking data. The same person, in fact, who was involved in correctly reassigning a different, earlier lunar impact IN 2022 that had initially been misidentified as SpaceX hardware before further analysis traced it to a Chinese Long March rocket stage instead. This time, the identification held. Once Gray's tracking calculations pointed toward an imminent moon impact, NASA's Jet Propulsion Laboratory ran its own independent confirmation through its Center for Near-Earth Object Studies and reported, in plain and unambiguous language, a 100% chance of impact. SpaceX's own director of NASA Science and Dragon programs, Juliana Scheiman, confirmed at a briefing that the company had been in direct communication with NASA as the object's trajectory became clear, tracking it together in the days leading up to impact. Now to what instruments actually managed to capture. It is worth being upfront that there is no dramatic video of the impact flash itself, and understanding why tells you something real about the physical scale involved. At a distance of roughly 225,000 miles from Earth, an object the size of a school bus striking the moon's surface, even at over 5,000 miles an hour, produces an impact flash far too faint and far too brief to be visible to the naked eye. And NASA's own scientists candidly noted the event would prove genuinely difficult to spot, even through professional telescopes. What did successfully capture something was the European Southern Observatory's Very Large Telescope, stationed at the Paranal Observatory in Chile. Using spectroscopy, the technique of splitting incoming light into its component wavelengths to identify the specific chemical elements present, The VLT detected clear spectral signatures of sodium and lithium gas rising from the impact site, a signal that persisted for roughly 5 to 10 minutes after the moment of impact, direct chemical confirmation that a real, energetic collision had genuinely occurred, even without a visible flash to accompany it. The genuinely compelling visual evidence came from a different source entirely, South Korea's National Space Agency. The country's lunar orbiter, Lunar, officially known as the Korea Pathfinder Lunar Orbiter, happened to be well positioned to observe the impact site directly, and its operators executed a coordinated imaging campaign around the event, capturing one photograph roughly 30 minutes before the predicted impact time, followed by 7 additional images taken over the following hours, continuing until around 7 in the morning, local time the following day. Those before and after images represent the actual real visual record of this event, not a dramatic video of a fireball, but a careful, methodical documentation of the lunar surface in that specific location, captured just before and repeatedly after the moment scientists knew with complete certainty that the impact had occurred. The scale of what those images and calculations are expected to eventually reveal is itself worth walking through, because the numbers involved are genuinely substantial for what was, ultimately, a piece of space debris rather than a purpose-built spacecraft. The upper stage, weighed in at roughly 8,800 pounds, measuring about 45 feet long and 12 feet wide, and it struck the lunar surface with enough kinetic energy to be compared, by scientists studying the event, to nearly 3 tons of TNT. Researchers involved in modeling the impact, including a team from the University of Texas at Austin who submitted a related paper to Geophysical Research Letters. Just days before the event, along with a separate preprint study involving NASA researchers, projected the resulting crater would measure somewhere between 60 and 90 feet across, with an estimated depth in the range of 12 to 16 feet. Confirming the crater's exact final dimensions will take additional time, since it requires follow-up. High-resolution imaging from a spacecraft like NASA's Lunar Reconnaissance Orbiter, comparing detailed before and after photography of the specific impact site to precisely measure what changed. It is genuinely worth pausing on how NASA scientists chose to frame the risk this event posed, because the framing itself carries real information. Officials were explicit that the impact posed no danger whatsoever to Earth, and offered a specific comparison to put the scale of the collision in perspective, noting that a meteoroid carrying roughly the same amount of energy as this rocket stage strikes the Moon from entirely natural causes, on average about once every 6 days. That comparison matters because it places a genuinely rare human-made event, one of only a small handful of confirmed unintentional rocket impacts on the Moon in the history of spaceflight, in honest context against the Moon's ordinary constant background rate of natural bombardment from small asteroids and meteoroids, a rate that has been reshaping the lunar surface for over 4 billion years regardless of anything humans have ever launched. That context matters for a second reason. Connected to a genuinely valuable side benefit researchers highlighted around this event. NASA scientists specifically noted their intention to use the impact as a live opportunity to refine tracking techniques for objects in cislunar space, the increasingly congested region between Earth and the Moon, where a growing number of active missions, historical debris, and future crewed operations are all expected to operate simultaneously. Carl Schmidt, a planetary scientist at Boston University's Center for Space Physics, who has studied similar past events, noted plainly that opportunities like this are rare enough in a scientific career to be genuinely valuable when they occur, offering real data on how the Moon's extremely thin, transient atmosphere responds to a sudden energetic disturbance, information relevant both to basic lunar science and to the practical challenge of understanding what any future impact, natural or artificial, might do to hardware or astronauts stationed on or near the surface. This event also connects directly to a larger, genuinely underregulated problem worth being honest about. This was not the first time a piece of rocket hardware has struck the Moon by accident, and it will very likely not be the last. A separate rocket body struck the Moon's far side in March of 2022, a case that initially generated real confusion, first attributed to a SpaceX Falcon 9 stage from the 2015 DSCOVAR mission, before further independent analysis by multiple astronomers, including Bill Gray and Jonathan McDowell at the Center for Astrophysics, correctly re-identified the object as a Chinese A Long March 3C rocket booster left over from the 2014 Chang'e 5T1 mission. The underlying issue both events share is straightforward and structural. Sending a payload to the Moon on a translunar trajectory typically consumes nearly all of a rocket stage's available fuel, leaving little to nothing in reserve for a controlled disposal maneuver afterward, whether that means safely deorbiting into Earth's atmosphere or deliberately steering into a stable, harmless solar orbit. Achieving that kind of clean disposal requires deliberately budgeting extra propellant into the mission design from the very beginning, a step SpaceX has voluntarily begun taking on more recent missions, including reserving enough fuel to place the upper stage from its November 2025 Escapade mission directly into a long-term solar orbit rather than leaving it adrift. As of right now, no binding international framework requires any commercial or government operator to plan for that kind of responsible end-of-life disposal on cislunar missions. Practices remain entirely voluntary, and tracking data suggests China's own Lunar launch program has, in recent years, similarly begun shifting toward placing spent upper stages into solar orbit rather than leaving them on trajectories that eventually intersect the Moon or Earth. But again, as a voluntary choice rather than a mandated standard, any launch provider is legally required to follow. NASA Administrator Jared Isaacman addressed the broader trend directly in remarks following this event, noting that the continued development and adoption of reusable rocket technology across the industry should naturally help reduce the frequency of these kinds of unplanned lunar impacts over time, since a fully reusable stage that returns to Earth never becomes a piece of drifting cislunar debris in the first place. So here's the honest, complete shape of this story. A real Falcon 9 upper stage really did strike the Moon on August 5th, 2026, tracked with total certainty in advance, confirmed by spectroscopic detection of vaporized sodium and lithium from one of the world's most powerful telescopes, and photographed before and after by South Korea's Danuri lunar orbiter. Genuine images of a genuine event, even without a dramatic impact video to go along with them. It happened because of a structural gap in how the entire spaceflight industry currently handles end-of-life disposal for lunar-bound rocket stages, a gap that is slowly narrowing through voluntary industry practice rather than binding regulation, and it offered real scientists a genuine, rare opportunity to study exactly how the Moon responds when something substantial hits it. That is a story that does not need any embellishment. The real version, tracked, measured, and photographed by real instruments, is already remarkable enough on its own. If you want to see the confirmed high-resolution before and after imagery, once NASA's Lunar Reconnaissance Orbiter gets a direct look at the new crater itself, subscribe and keep notifications on, because that comparison, the clearest evidence yet of exactly what this impact actually left behind, is still on its way.